In this video, we're going to practice solving some very basic differential equations. So here are the directions for the first problem I'm going to work through. Find the general solution of the differential equation y prime of t equals 5 plus e to the negative 3t. Okay, so first of all, why is this considered a very basic differential equation? Well, first of all, I'm just dealing with a first derivative, which makes it pretty simple. The only derivative that appears is this y prime of t. This is also what's called a linear differential equation. This first derivative isn't squared. It's not being multiplied by y or anything like that. It's just the plain old first derivative. And also, this is kind of already laid out in a nice form. Sometimes you'll have the derivative mixed up with some of the other terms in the problem, but this is just y prime of t equals something. So this makes it a very straightforward differential equation to solve. Okay, so just a reminder, when we're solving differential equations, what we're doing is we're trying to find the original function. So I'm given an expression here that involves the derivative, but I want to figure out what y of t, the original function, actually satisfies this relationship. Okay, so let's just dive right in and solve this problem. So the way I'm going to approach this is, so I know y prime of t, and I want to find y of t. So you can probably guess that we're going to be using integration to solve this differential equation. And what I'm going to do is I'm actually just going to integrate both sides of this equation with respect to t, since t is my independent variable in this case. Okay, so I'm just integrating both sides with respect to t like this. Now on the left-hand side, if I integrate y prime of t, I'm just going to get y of t. So y of t equals, okay, so now I need to integrate this function 5 plus e to the negative 3t. So here's where you're going to have to remember your rules of integration. So if I integrate 5, I should get 5t, plus, if I integrate e to the negative 3t, I should get negative 1/3 e to the negative 3t. So how did I know that? Well, there's a few different ways. One, you may have just memorized a formula for things of the form e to the at power. Or alternatively, you could think of it as a U-substitution. So just really quickly, if I were to let u equal negative 3t, then du, the derivative, would be negative 3 dt. Or I could write that as negative 1/3 du equals dt. So that's where this constant of negative 1/3 comes into play. Okay, so this is my antiderivative. I need to remember to add a plus c. So I could add any constant to the end of this, plus 2, plus 3, minus 5, etc. And its derivative, y prime of t, would still be 5 plus e to the negative 3t. So just remember that plus c. And this actually is our answer in this case. We just found y of t. This is called a general solution because it includes the plus c in it. So this represents a whole family of solutions to the differential equation. And you should always just verify your answer. You can do this just really quickly in your head for a lot of problems. Just glance at this, take its derivative, take the derivative of y of t, and just make sure you get back this y prime of t. In this example, we're also going to solve a fairly straightforward differential equation. But this time we're going to be working with a second derivative. So the instructions are to find the general solution of the differential equation y double prime of t equals 13e to the 6t minus cosine of 2t. So how am I going to approach this problem? Well, remember my goal is to solve for y of t. Now what I'm given here is I'm given the second derivative. So what I want to do is I want to integrate to find the first derivative, and then integrate again to find the original function y of t. So that's what we're going to do here. So let's start by integrating both sides of the equation. So if I integrate y double prime of t, I'm going to get y prime of t, or the first derivative. So the first derivative equals, and now I need to integrate this expression 13e to the 6t minus cosine of 2t. So this is where you need to remember some derivative rules. So if I integrate 13e to the 6t, I'm going to get this constant 13 to stay out front. Now when I integrate e to the 6t, I'm going to get a factor of 1/6. So this is going to give me 1/6 e to the 6t. Now if you need to convince yourself of that, just do a little U-substitution out to the side. But once you do enough of those, you'll kind of just get used to the form. Okay, minus. Now hopefully you remember the antiderivative of cosine is sine. But since this is cosine of 2t, I'm going to have this factor of 1/2 out front. So minus 1/2 sine of 2t. And once again, if you need to convince yourself of that 1/2, just do a little U-substitution on cosine of 2t out to the side, letting u equal 2t. And you'll see really quickly where that 1/2 comes from. So now I need a constant of integration. I'm going to write plus c1. Now the reason for this will become more apparent as we go through the problem, but what's going to happen here is because we're going to be integrating twice, we're going to end up with two constants of integration. So I want to distinguish those, so I'm going to call this one c1. Okay, so this is y prime of t. So now I'm just going to do the same thing again to find y double prime. I'm going to integrate both sides of this equation. So I'm going to be integrating 13/6 e to the 6t minus 1/2 sine of 2t plus c1. So if I integrate y prime of t, I get y of t. So 13/6, well the 13/6 is going to stay around, but I'm going to get another factor of 1/6 when I integrate e to the 6t. So 1/6 e to the 6t again, minus, so my 1/2 stays, but when I integrate sine, I should get negative cosine, and also another factor of 1/2, so negative 1/2 cosine of 2t. Then I have my plus c1. Now remember that's just a constant like 2 or 3. So when I integrate that, I should get plus c1t. And then I need to remember a constant of integration, so plus c2. And finally, I might just clean this up a little bit. So I can write this as 13 over 36 e to the 6t plus 1/4 cosine of 2t plus c1t plus c2. So once again, this represents a whole family of solutions to the differential equation. c1 and c2 can both be any constant, and they can be different constants. So this right here, what we just found, is the solution to our differential equation. And you can check yourself. If you took the second derivative of this function, you should get this y double prime of t that we started with.